students, welcome back to another lecture in our course Environmental Modeling and Simulation. Today we are going to discuss Lotka Volterra model of competition. So let's get started. When we talk about Lotka Volterra model of competition, we need to select two species that are competing with each other. Please note that Lotka Volterra model of competition is a very good building block when we are making more complex, more accurate models that are perfect for a particular situation. And the model of competition between species that we use now are improved versions of Lotka Volterra model. This is an old model, but it is a very good teaching tool and it is still important to understand it. For our example, we are going to take example of rabbits and sheep. So, representing rabbits with R, representing sheep with S, and we want to know how rabbits and sheep will behave, how the numbers will grow or decrease in a closed ecosystem. Now, why have I decided that we are going to go with a closed ecosystem? Because I want to control the variables to make my model very simple. As I said in one of the introductory lectures, that environmental systems are very complicated because there are so many variables that affect each other. We are going to isolate them. We are just going to be with rabbits and sheep, and they are going to compete for grass. So, in a closed system, we have rabbits and we have sheep, and they are competing for vegetation to eat. Now, the assumptions are that there are no predators. So, we will not have hyenas and wolves and foxes hunting rabbits and sheep. We do not have humans hunting them. The other assumption is that since this is a closed system, the amount of grass is the limiting factor to their growth. So, rabbits cannot multiply to infinity, sheep cannot also keep growing indefinitely because grass, the main food, is limited. The other thing that we are assuming is that rabbit and sheep only compete with each other, they are not actively hurting each other. Okay, so we are going to write models for dr by dt, which is the rate at which the population of rabbit is changing, and ds by dt, the rate at which population of sheep is changing. Now, the rate at which the population of a species or some entity changes depends upon two things. One is the net growth rate. So, net growth rate will account for birth and death in case of bacteria for cellular division, and then the natural process of dying of the bacteria. And then it also depends upon any other factor that is going to influence the overall growth rate of rabbits. We will do a similar system for sheep. Now, let us try to understand. In case of rabbit, the net growth rate will require one of the growth models that we have studied. Remember, we have studied three growth models: exponential, Gompertz, and logistic. Now, here once again logistic model makes most sense because logistic model assumes limitation of resources, which is one of the assumptions made in this closed system, that the grass is not infinitely available, it is a limited resource. So, for net growth model we can use the logistic equation. Same thing with the sheep. For the net growth model we can use the logistic equation. Now, when it comes to any other factor that is influencing the rate at which rabbits and sheep multiply, clearly we are talking about modeling the competition between two species. Any other factor that is affecting their growth rate for both rabbits and sheep would be competition. So, the any other factor here is competition. So, we are going to model the competition. So, let us first write the model for net growth rate based on logistic equation. So, we will start with rabbits and write sheep here little below. So, we have space. Now, we know that the logistic growth model will look something like this: Rx minus x square, where R is the growth rate, x square tells me about the relative levels of animal that the ecosystem can handle. Now we know that rabbits are famous for how fast they reproduce. So let's use a big number for their R. Let's say 3x minus x squared is the logistic growth model for rabbits. On the contrast, sheep take much longer to grow compared to rabbits. So for sheep, we can write a more humble growth rate, 2y minus y squared. Okay? Now we need to write the competition term. So plus or minus something competition term. So let's take a moment to think about what the competition term should be. So in order to write the competition term, we need to understand better what is happening on the ground. When rabbit and sheep are grazing on the grass, let's say rabbits are happily munching off the grass, then when the sheep come to graze, what they'll do is they will nudge the rabbits away, and then they'll not leave space for rabbits. They'll push the rabbits away, and then they'll eat the grass. So competition happens when rabbit and sheep interact with each other. Let's say rabbits are eating grass at one end of the ecosystem and sheep are consuming grass at the other end of the ecosystem, then they are not really competing. They're using the resources in a separate way. They're not interacting with each other. Competition in this sense can be defined when they are competing for the same area of grass, same patch of grass. So competition in this sense requires the rabbit and sheep to interact. In modeling, whenever two entities interact with each other, we use the principle from probability and we multiply their numbers. So if there is any phenomena, let's call it phenomena 1. And this phenomena depends upon the interactions between, let's say, species 1 and species 2. So the one way to model this phenomena would be to put a constant, some constant, and multiply the number of species 1 and species 2. I told you that this is derived from probability. How? We are looking at the product of number of two species. We are looking at the probability of these two species to interact with each other, which will be proportional to the product of the numbers. So basically the competition term will be some constant and the product of the two species. So we are going to get this competition term to look something like A rabbits into S, in this case B rabbits into S. So the more rabbits, even if we have just 2 or 3 sheep, but we have lots of rabbits, they are going to interact more frequently. If we have 2 rabbits and 2 sheep, their product is going to be much smaller compared to when we have 20 rabbits and 10 sheep. So the product is very important. Now the other thing we have to look at is what the constant will look like and what the sign of this competition term will look like. Now if this particular phenomena, which in this case is competition phenomena, was beneficial for a species, then it will help the growth rate go up. In that case, we want to use positive sign. Here the competition is not helping the number of rabbits to go up or the number of sheep to go up or increase their dr by dt or ds by dt. In fact, it's having a detrimental effect on their overall growth. So clearly we are going to stick with minus term. So I'll clean this up and just put the minus term. Okay. Now I told you that competition term will look like ARS and BRS, so let me clean that up. Okay, now what is the value of A and B? Now think about it this way, when rabbit and sheep interact and the sheep are nudging rabbit away and rabbit are trying to go between the feet of sheep and trying to find their patch of grass, their blade of grass to eat, who is going to suffer more? Are rabbit going to suffer more or are sheep going to suffer more? Now I am assuming since sheep are much bigger than the rabbits, it's the sheep that are going to overpower rabbits way more than rabbits can overpower sheep. So the rabbits, let's say, are going to suffer twice as much as the sheep are going to. So what we can do is, again, this is a very rough model. I am putting the numbers arbitrarily. Typically for understanding or finding out the, if you don't have very good in understanding of the phenomena, like I know for example the rabbits will suffer twice as much as sheep, then what I can do is I can very quickly make sure that my constant here is twice and the constant here is 1. Yeah, but in absence of this understanding, this exact precise understanding, we need to do data fitting to understand what the parameters are, or we need to have some really good theoretical understanding of what the parameters are going to be. Here I am using them arbitrarily. This is not how we do modeling, right? But this is to help you understand that even the constants, even the parameters are important. For example, rabbits grow much faster than sheep. So, here the growth rate is to the power 3. Here the growth rate is to the power 2. Rabbits suffer twice as much as sheep. So, I am putting 2 here and 1 here. Okay. So, for now let us use this model. Again, do not get very finicky about the constants, the parameters that, sorry, the constants I am using. This is just to give an example. All right. So, this is the model that we have come across. And the take home message that I want you to remember from this particular slide is that if you remember the introductory lectures, first we make the conceptual model and then we write the mathematical equation or expression. Which is this one here, okay. That is exactly what I am doing, that is what I wanted to demonstrate. And then in this case we are going to explore how to analyze this mathematical expression using graphical approach. Remember, the first step in using graphical approach for qualitative analyses of the model, we are going to find out the fixed points. Oh, by the way, there is an obvious mistake here which I hope you have figured out, and the mistake is I am using x instead of r. Small typo. I am glad, I really hope that you figured this out way before I did. Okay, we are going to find the fixed point. So, step 1, find the fixed point. So, remember, fixed points are when there is no change with time. So, dr by dt and ds by dt will simultaneously become 0. So, what we have is 3r minus r square minus 2rs is equal to 0. Now, this seems like quadratic equation, and in some ways it is. We can take r common in the first equation and s common in the second. So, we are left with okay. So, now when we are in this situation, the first possible solution that we look at is that r is equal to 0, r is equal to 0. So, when r is equal to 0, then we can substitute r equal to 0 in the second. So, let us call this the first equation and the second equation. We can substitute r equal to 0 in the second equation, and then we are left with s is either equal to 0 or s is equal to plus 2. Yeah. Now, the other possibility is that r is not equal to 0, but s is equal to 0. When s is equal to 0, then what we have is we can put s equal to 0 in the first equation, and then r is either equal to 0 or r is equal to plus 3. The next possibility is that neither r nor s are equal to 0. So, in this case, since r and s both are not equal to 0, this situation, these two terms 3 minus r minus 2s and 2 minus s minus r, they have to be 0. So, we will solve them. So, let us solve them. So, we have 3 minus r minus 2s minus 2s equal to 0, 2 minus r minus s equal to 0. We can subtract these terms. 1 plus 0 minus s equal to 0, s is equal to 1. When s is equal to 1, we can substitute this in any of this equation and we will get r is equal to 1. So, when r and s are not equal to 0, then r s is equal to 1 1. So, basically we have 4 fixed points. One is 0 0 when both r and s are 0. The other is r is 0 and s is not 0, so which is 0 2. Next is s is 0 but r is not 0, so we have 0 3. and then we have 1 1. So, we have 4 fixed points here. So, we are going to get one Jacobian matrix and we are going to get 4 characteristic equation. We are going to find out the behavior of trajectories around each of the 4 fixed points. Before we proceed there, just take a look at the 4 fixed points. What are they telling us? 0 0 is a fixed point when in our ecosystem we have neither the rabbit nor the sheep. Yeah, so this is RS, just to be clear. Neither the rabbit nor the sheep. It's a fixed point because if there are no rabbits and sheep to begin with in the closed ecosystem, they're not going to grow. The second fixed point is saying that, hey, there are no rabbits, there are only 2 sheep. What this is telling me is that in case for some reason the rabbits vanish out, we have no rabbits, then the number of sheep will be 2. It's a fixed point, and in case it is a stable fixed point or has a stable manifold, then we know that the number of sheep will somehow stabilize around 2. The third fixed point, oh, I'm sorry, I have written these 2 fixed points in a wrong way. No rabbit, 2 sheep, no sheep, 3 rabbits. Okay, these are the 4 fixed points. Okay, so the third fixed point is saying that in case for some reason the sheep vanish away, then the ecosystem will support 3 rabbits. You can see already this is sort of making sense. If only one species is existing, then we will have more rabbits, 3 units, compared to sheep, 2 units. The fourth fixed point is a fascinating fixed point because it is the only fixed point where both rabbits and sheep are coexisting. So, right here we are talking about mutual extinction. They are not there to begin with, or they both of them die. Here we are talking about rabbits going extinct. Here we are talking about sheep going extinct. And here we are talking about coexistence. Now we have been talking about biodiversity loss, climate crisis, and the subsequent impact on our biodiversity, on our flora, on our fauna, and how species are going extinct faster than ever before, and we are actually in middle of 6th mass extinction. So, we are here, one of the species is going extinct, or some species are going extinct and few are surviving. What we want is coexistence. So, this is a very important model. All right, let us go ahead and write down the Jacobian. So, remember for Jacobian what we are going to do is we are going to do partial derivatives of the systems with respect to R and S. So, the first is 3R minus, let me write this down, 3R minus R square minus 2RS. Let us call this function f. Okay, let me confirm. Perfect. Alrighty, so our Jacobian is going to look like this. Let us write the Jacobian. Okay, this is our Jacobian. Now, we are going to go through each of our fixed points and we are going to find our characteristic equation. So, the first fixed point is 0 0, the rabbits are 0, sheep are 0, and the characteristic equation we end up with is 3 0 0 2. Now, let us look at the tau. Tau is 6, delta is 6, tau square minus 4 delta 36 minus 24 greater than 0. The tau and delta are in the first quadrant outside the curve in this equation. So, we are dealing with unstable node. Right here you can already understand why this is an unstable node, because when we are in the neighborhood of this unstable node, if we have 2 sheep, 2 rabbit, which is a small number of sheep and rabbit for an ecosystem, their tendency is to move away from 0 0, because life wants to go on. So the sheep and the rabbit will multiply. So no wonder 0 0 is an unstable node. Let's look at the other fixed point, which is 0 rabbits and 2 sheep. So A 0 2. Our characteristic equation is so here our tau is -3 and delta is +2. And we are outside the curve. So tau is negative, so either third or fourth quadrant. Delta is positive, so we are definitely in the fourth quadrant. Outside the curve, we are dealing with a stable node. So this is a stable node. So unlike 0 0, which is when both species are not there, which is unstable because life wants to move on, extinction of rabbits is actually a stable node. So given the right circumstances, there is a chance that rabbits will go extinct. Let's look at what happens in the fixed point where the sheep are going extinct. So we find the characteristic equation by putting the value 3 0. Okay, so this is our characteristic equation. The tau here is -4, delta is +3, tau square minus 4 delta is 16 minus 12 greater than 0. We are again dealing with a stable node situation. So extinction of sheep, evolutionary victory of rabbits in this system is also a stable node. So given right circumstances, there will be a strong tendency to go towards this stable node and to stay there. So once, basically what this is also telling me is that once rabbit go extinct or once sheep go extinct, that's a stable node, they're never coming back. However, or if once the sheep reduce enough that they are coming closer to extinction, then they will go to the extinction. Once rabbit come close enough to go to extinction, they will go to extinction unless we change the ecosystem. Now let's look at our last fixed point, which is 1 1, coexistence. So this is an unstable node. Both extinction fixed points are stable. So if we are in the neighborhood of this fixed points, close enough to this fixed point, and this enough depends, qualitatively we can only use words like close enough, neighborhood, then one of the species will go in extinction. So let's look at coexistence. So we are talking about characteristic equation around the fixed point 1 1. Alrighty, the tau is -2, tau is negative, delta is also negative, and since delta is negative, tau is negative, we are in the realm of saddle point. I do not even need to find out tau square minus 4 delta. So we are in the realm of saddle. So even before finding out the eigenvector and eigenvalues, which will be very important to do for the saddle node. So I already know how the system is going to behave. Very quickly, the phase portrait will look something like this. One fixed point is 0 0. It is an unstable fixed point, so the trajectories are moving away, life wants to move on. Then we have r on x-axis, s on y-axis, by the way. Then we have a stable fixed point 0 2, where rabbits have gone to extinction, but sheep, we have 2 units of sheep available, 0 2. This is a stable node. So again it is attracting. Let me draw this little far away so that you can see the trajectory slightly better. So it is attracting trajectories towards each other. This is repelling the trajectories away from each other. Then we have the third fixed point where sheep are driven to extinction and rabbits still survive. This is also a stable fixed point, which means again it is attracting trajectories towards each other. Again, I have not drawn the curved trajectories because I do not know the eigenvalues and the eigenvector. Then we have a humble fixed point here 1 1, which is a saddle, which means given the right situation there is a possibility that it will attract towards coexistence, but depending on our initial point it might repel towards extinction. So I know even before I find the eigenvalues and eigenvector, I know this is how the behavior will look like. So now let's go ahead and find the eigenvalues and eigenvector. First I want to find out for saddle point. Today we only have time to find out the eigenvalues and eigenvector for the saddle point, which is the coexistence point, and then tomorrow we will find out for the stable points also and the unstable fixed point, and then we can put the phase portrait together. So this is our characteristic equation -1 -2 -1 -1 for our saddle. Okay, so from here we have lambda square plus 2 lambda plus 1 minus 2 is equal to 0, lambda square plus 2 lambda minus 1 is equal to 0. So lambda is equal to minus 2 plus minus 4 plus 4 by 2. We are getting minus 2 plus minus 2 root 2 by 2. So lambda 1 lambda 2 is equal to minus 1 plus minus root 2. So we have two eigenvalues. What we can do is we can go ahead and find out the eigenvector corresponding first to minus 1 plus root 2. So what we see here is minus root 2 V1 is equal to 2 V2, and this will be the case for both of them. So we get V1 by V2 is equal to root 2 minus root 2 by 1, and even with this you will get the same. So the corresponding eigenvector for lambda 1 is basically minus root 2 in x direction and then 1 in this direction. So it looks like this. Now I already know how the phase portrait is going to look like. So let's make room. Okay. So corresponding to the second eigenvalue, which is lambda 2 is equal to minus 1 minus root 2, our eigenvector, let's find it out. Alrighty. So very simply what we get is that V1 by V2 will be equal to root 2 by 1. So these are the two eigenvectors that we have gotten. Briefly, our phase portrait will look something like this. At 0 0, unstable node. At 0 2, this is sheep, this is R, stable node. 3 0 stable node. 1 1 we have two eigenvectors, one is in this direction, the other is in this direction. So, roughly let's do with this one, the positive eigenvector minus root 2 and then 1. So, minus root 2 here and then 1 units here. So, this is the positive one, it is the repeller, and then so this is lambda greater than 0, lambda minus lambda which is negative, which is less than 0 is root 2 by 1. So, root 2 units here, 1 here. So, in this direction, and it is the attractor. So, basically how our phase portrait is going to look like, I am going to draw roughly in green, and in the next lecture we will discuss it, something like this. Okay. So, this is how our phase portrait will roughly look like. In the next lecture, I am going to give you the eigenvalues and eigenvector for the 3 stable fixed points. We will draw a more better looking phase portrait. It will be quite similar, and we are going to discuss how difficult, how sensitive coexistence is and how easy extinction is. We are also going to discuss the idea of basin, about how the stable and unstable manifold can separate the phase portrait into two different basins. All right, students, this is all for today. See you in the next lecture. Thank you.